11.1 sequences and series. We start with a sequence, and a sequence is some function that produces an ordered list. So you're going to have like a list of terms, a list of numbers. A finite sequence, okay, finite is countable. And so if the sequence stops like this, 1, 2, 3, there's a finite sequence right there. You've got 3 numbers in that list, all right? But an infinite sequence is one that doesn't end, and so it'd be like 1, 2, 3, ... Okay, so a finite sequence ends and is countable. Infinite never ends, isn't countable. Number 1, you're going to know how to do this, I think, already. Example 1, write the first 5 terms for each sequence. So when they give you an equation like this, a sub n is talking about just whatever term, the nth term. And so if you want the first term, you'd plug in a 1. A1 is 5 times 1 minus 2. All right, so that's going to be 5 minus 2. That's going to be 3. And then they want the first 5 terms, so let's find the second term. A2 is going to be 5 times 2 minus 2. Now notice where n is. I'm just plugging in that n number right there. That's going to be 10 minus 2, which is 8. And then we can do A3. A sub 3 is 5 times 3 minus 2. It's 15 minus 2 is 13. And at some point, you're going to see a pattern. It looks like I'm just adding 5 to the next number. So you can tell the next number is going to be 18 without even doing the math. But let's go ahead with it. A4 is going to equal 5 times 4 minus 2. That's 20 minus 2. That's 18. And the fifth term, A5, is 5 times 5 minus 2. 25 minus 2 is 23. Okay, so there are my first 5 terms. Let's go ahead and wrap it up like this and say 3, 8, 13, 18, and 23. Those are my first 5 terms. So then the next one is a little bit more complicated looking equation, but it's the same idea. You're going to plug in 1 for the first term. So a sub 1 is negative 1 to the 1 plus 1 times 1 squared. I'm plugging in 1 everywhere it says n. Negative 1, that's negative 1 squared right there. Negative 1 squared times 1 squared is 1. Negative 1 squared, of course, is 1. You have 1 times 1, which is 1. The second term, a sub 2, you're going to plug in 2 everywhere it says n. So that's negative 1 to the 2 plus 1 times 2 squared. That's negative 1 to the third times 4. So negative 1 to the third is just negative 1, so that's negative 1 times 4, that's negative 4. Now we do A3. Negative 1 to the 3 plus 1, that's going to be 4 times 3 squared. Negative 1 squared is 1. You're going to have times 3 squared. That's 9. Let's do A4. You're going to have negative 1 to the 4 plus 1, so that's the 5th power, times 4 to the 2nd power. Negative 1 to the 5th is going to be negative 1 times 4 squared. That's going to be negative 16. And then A5 is negative 1 to the 5 plus 1, which is 6th, times 5 squared. That's going to be 1 times 25 is 25. So if you look at it, you've got a list of terms: 1, negative 4, positive 9, negative 16, and 25. Part C looks pretty complicated, but it's basically the same idea. We want to find those first 5 terms. So A1, don't have a lot of room here, so write small. you've got 3 times 1 plus 2 over 1 squared plus 3. Okay, so order of operations, 3 times 1 is 3, plus 2 is 5 on the top. On the bottom, you'd have 1 squared is 1, plus 3 is 4 on the bottom. So that's 5/4. Let's look at A2. A2, you're going to have 3 times 2 plus 2 over 2 squared plus 3. Again, I'm just plugging in 2 in for n everywhere in that equation. 3 times 2 on the top, that's 6, plus the 2 is 8. On the bottom, 2 squared is 4, plus 3 is 7. Let's move on to A3. A3, plug in 3. You have 3 times 3 plus 2 over 3 squared plus 3. On the top, 3 times 3 is 9, plus 2 is 11. On the bottom, you have 3 squared is 9, plus 3 is 12. A4. 3 times 4 plus 2 over 4 squared plus 3. 3 times 4 is 12, plus 2, that's 14. And 4 squared is 16, plus 3, that's 19. Last one, A5. 3 times 5 plus 2 over 5 squared plus 3. 3 times 5 is 15, plus the 2 is 17. 5 squared is 25, plus 3 is 28. So there are my 5 terms. Let's just wrap that up and write them all out. First term was 5/4, and then 8/7, and then 11/12, 14/19, and 17/28. Convergent. Convergent means we're going to get closer and closer to some real number. And what I mean by that is as you look at the numbers in the list, okay, the numbers are going to change. Next number, next number, next number. If those numbers are getting closer and closer and closer and closer to the same number, that's convergent, okay? If they don't, that's divergent. So does not converge. Okay, let me try and think of an example here. Let's say I have, let's say I go 8, 4, 2, 1. Can you see that I'm just cutting the number in half, right? Okay, next number would be 0.5, and then 0.25, ... That sequence is going to converge because it's approaching some number. What number does it appear to be approaching? It appears to be approaching 0, right? That would be convergent, okay? That would be convergent. But something like if I did 1, 2, 4, 8, ... Those numbers are getting bigger and bigger and bigger. I'm doubling them every time. That's not going to converge to some number. Okay, so that would be divergent, all right? So convergent, it's getting closer and closer to some number. Recursive definition is defined using previous terms So what you're going to see is like if they are defining the nth term, a sub n, they're going to use like the term before that might be n minus 1. So let's say we have a sub n equals a sub n minus 1 plus 2 or whatever, okay? They're just taking the last term and adding 2 to get the next term, okay? An explicit definition is defined usually using n. and not the previous terms. So a sub n might be 3 times n plus 4, okay? So I don't need to know the previous term to find the next term, all right? The explicit definition sometimes is better for us, because if I wanted to find the 100th term, all I would have to do is plug in 100 into that formula. Whereas a recursive definition, if I wanted to find the 100th term, I would have to know the 99th term. And if I wanted to know the 99th term, I'd have to know the 98th term, and so on and so on. Fibonacci sequence, you've probably seen this before. 1, 1, 2, 3, 5. Does anybody know what number comes next in this sequence? 8, very good. And then what? 13. How are we getting the next number in this sequence? Adding the previous 2. So this seems like a recursive sequence right here. 21, 34. You just keep adding the previous 2 terms to get the next term. Fibonacci sequence.